This session is designed to give us a little bit of background in network visualization. It's a little bit of dessert after a long day of working on other stuff, and so we'll do this. And then in your great joy, you get stuck with me for the lab section of this as well afterwards, where we're going to go through a series of examples on both how to do visualizations and to do some of the community detections and answer some of the points that Peter made about the trade-offs between software and such. So I said at the very beginning when we were introducing the network models that this field has been rooted in a visualization for a long time. It's been a core, this visual imagery has been a core part of the network analysis field since the 1930s. And what you're seeing coming up on the screen behind me here are a series of some of these early visualizations that came out in the 30s and 40s, and some of them are just fascinating and really fun from an archival standpoint just to go look at. But the reason that we cared about visualize, remember, was this idea that Moreno had, was that we have this notion of these intangible structures, these things that affect behaviors, and we want to be able to make them real. We want to see them so that we can analyze them in some rigorous way. And so that's the goal of doing visualization. The history is long, and if you think about where this came from, the whole root of network analysis is in original graph theory, and Wheeler had this wonderful problem, which are the 7 bridges of Königsberg, where you had to try to figure out if you could trace a single path across the bridges that never went over the same bridge twice. And so this is, look at it for a while and play with it, and it's a kind of a tough problem. Like, how do you do this? It seems like it's got to be a simple way to do it. And it turns out, of course, that if the river looked like this, it would be easy. I would just go to the left, go to the right, go to the left, go to the right, right? If it's a line, it's not hard to do. But when you have a setting that looks a little more like this, where there's an island in the middle of these rivers, and the river then splits, so you get these different branches, you need some way to abstract from the actual geography to get something that's useful. And that's where graph theory actually came from, all right? And so the idea is once I could abstract from these notions of islands or land masses to bridges, I'd have a formalism that would let me think about how these things work. And being able to do a walk on this actually is, it turns out it's impossible for this particular configuration to not cross the bridge at least once. But this was this first idea that by thinking about something not as the problem as is given, but as a level of abstraction. So it might be one thing to think about relationships as the kinds of things that we are deeply invested in and care about and talk about all day. But instead we could abstract to them and simply be points and lines, and we might learn something, right? Something different, anyway, than we would if we just talk about them. Some of the earliest visualizations that you might be familiar with are kinship trees, right? So this is some of the early kinship diagrams by Morgan, where you have, in the Western system, you have great-great-great-grandfathers down the line of descent and so forth. You have bureaucratic trees. This is the Russian Politburo, or some early version of that. It looks a little bit like Duke's administrative structure. This is the office of the provost, and this is everybody else. And I've been trying to get a copy of the Duke who reports to who, the actual tree, to graph it, and they won't give it to me. I think they're embarrassed of it. But that's that. The kind of things that we care about, where you move from those formal relations, either through kinship or through reporting structures, to informal relations, was Moreno's work. And some of his things that he did that was really interesting is he started immediately with multilayer networks. So you had different kinds of relations layered over the same set. And he ended up treating positive ties in red and negative ties in black. And if you look at this one school of little cabin of runaway girls in New York at the time, you see that there's this one person, CM, that is disliked by everybody, has one best friend that's reciprocal, who's friends with somebody who dislikes her, right? So if you're wondering why she's having trouble in school, it might not be hard to figure out that you want to figure out, like, why is it that everyone is disliking this person, and what might we do about it in terms of the patterns of relations. These are young kids, these are 6th graders, and these are boys in triangles and girls in circles. And as is true for 6th graders today, they are not friends with each other, right? And so this sense that because when you're in 6th grade, girls are still yucky, is the idea, or at least boys are. Girls, it's hard to know. So in any event, this is the idea, was that as soon as you plot it down, you know the story, right? And so you can get past the initial things and start thinking about new things. He expanded this idea. This is from one of his, so that first image I showed you was one of these cabins, and this is all of the cabins for runaway girls in this one institution in New York. And this was a giant 3 by 5 foot poster done in 3 colors for like, dislike, and I think hang out with or tell secrets to or something like this. And it was a sort of a remarkable attempt to scale up. It didn't work so well. It's really hard. This is a hard process to do with pen and paper and rulers in any way that's useful, because it turns out that beyond a certain scale, you need some way to make sense of these relations other than just putting them on the screen and hoping you get it right. And so what do we do instead? So as the field evolved, we came up with a few of these. These are some ideas that were out in the 40s. These were household level surveys done in a small village in New Hampshire, if I remember correctly. And so this is the mayor's house and everyone that's friends with the mayor's household and friends of friends. And it sort of there are these beautiful images from sort of a modern art almost standpoint. And what was amazing about this book, if you ever want to go and do it, is that all the lines going off the page are accounted for coming into the next page. So this was actually one giant hand-done diagram, and they were very careful about going through and making sure that if there were 15 ties coming out from this set, there would be 15 ties coming in from this side, right? And so those of you that are RAs that think that you're having a bad day and you're not having a lot of work and it's no fun, you could have been doing this instead. Now, once you start getting nodes and maps and lines, you like to do what we always do with maps, which is layer more information on them. And a common thing to do is to layer some kind of information on top of the nodes. Here, it's the number of times you're visiting family versus non-family in the same kind of a household village. And the idea is you can use a pie chart to represent the amount of things you have. This is just like what Peter showed, with which house people lived in the Caltech network. It turns out that it's only been in the last few years that the software easily does this now. It was actually, this is kind of a pain in the neck to actually generate this kind of a diagram. I don't know what Peter used for his, but it's a little complicated. The other thing that all of these early diagrams had in the 40s and 50s, they were just driven, they were written entirely, there was just as art. There was no science behind where nodes were put down, except for the idea, the general notion that you put nodes close to each other and you tried to avoid a bunch of lines that were going all over the place. And so people just sketched these by hand and tried to figure out a right way to do it. And if you're on your 3rd draft of this and you got a little tired of it, you just got lazy and put people on the side and moved them on the inside, right? And people started worrying about, is there some way that we can put some science on top of the art of this so they aren't completely haphazard? And this came up with this idea of a target sociogram with not the way. The idea here is that we take centrality, those ideas that Molly was talking about this morning, and we make the most central nodes in the middle, and then we radiate out through levels of closeness. And this was part of what we've seen in the network canvas tool that Jimmy and Patrick were talking about on Tuesday. And in this case, we distinguish it between boys on one side and girls on the other. And so for this one ego network, or for this one school, excuse me, we can distinguish that these are mainly girls that are talking to each other. They have a few boys that are also in their network, but they're not as central and so forth. And so you can get some notion of a direction that's built through that and some importance by this target idea. And if you decide you want to get cute, you can add faces, right? So they're boys or girls and they have bows in their hair. This is the algorithm for laying nodes out at the time. It's a pegboard with rubber bands. And so you do it by hand, and once you get them where you like it, you call it done. There's a 3D version of that where they put rubber bands on abacus. They took like a series of abacusi, and stacked them into a matrix, and you put rubber bands between the different beads. As you might imagine, not many of us are doing it, so it didn't work that well. But this notion that you might imbue meaning on an axis is endemic, and people keep coming back to it. And it doesn't work very well with lots of networks. And we're going to talk about a particular kind of network where it does work. But in general, if you have something like, in this case, socioeconomic status on the y-axis and peer group on the x-axis, you end up usually with a mess, right? Because social relations are never clean enough for that kind of an axis to work right. But there are some nice attempts to make these things global. This is just a beautiful picture that came out of some early work on trying to map the internet. Of course, once you get these things and the rise of networks recently, these things have gone from even artistic to now kind of silly. So this is an ad for hand lotion. And the idea is that this person is very happy, and she tells all her friends who tell her other friends and so forth, and there you go. They show up in popular culture from time to time. This is a New York Times image of business school leaders on Wall Street and the schools they went to. This is my least favorite, but sort of telling example. These are causal relationships amongst the war in Afghanistan. And if you wonder why you should never go into a war in Afghanistan, this is tell you why, right? And so the notion is that it's just an absolute mess, and it's not clear to me that you're going to learn a whole lot from an image like this, other than that it's a mess. And of course, then there are just spoofs on the real thing, right? And so this is my favorite image of Your Friends Make You Fat, of the Christakis finding, which was published in this set. And of course, unless we think that journalists are the only ones that make bad network images, you can find a bunch of these kinds of awful hairballs in the published literature, right? So this is an actual graph showing something in a network in a published paper. And if you can interpret anything about this that's meaningful, it's surprising. And so they end up becoming Rorschach tests as to whether or not there's something here. Maybe I can squint and see a cluster. Maybe there's some people on the edge. And so our goal today is to talk about how we might distinguish an image like this, which none of you should ever put in a paper, right, from an image that you might actually communicate something to an audience, right, in a way of thinking about networks and network visualization that allows us to learn something, and hopefully not something that's just artistic, but is also at least a little bit scientific. And so then how do we do that? The goal is to make the visible invisible, and we're going to try to take this portion seriously. And then to do that, we have to ask ourselves the first basic question: why are we visualizing at all? And so this is one of my favorite examples. This is a well-known issue. If you have a classic regression problem, I have an independent variable, 3 different dependent variables in this case. If I run a regression of y on x across these 3 different cases, you'll get this summary statistic set for all 3 series, right? So they're numerically exactly the same from a summary standpoint. You get the same r square, you get the same slope, you get the same sum of squares, and so forth. Right? But if you plot them, you look at this is what you might expect. It's a positive correlation, right, between x and y. You get a nice sort of line that goes through, a scattering around the line. Right? But this line fits perfectly as well, as does this one, right? And so by visualizing it, I can see immediately that these patterns are not as nicely represented by the regression line, right, as this one is. And the reason is because the visual thing that we're seeing when we look at this kind of a graph is we're not just seeing the slope, and we're not just seeing one axis. We're not just seeing a single dimension. We're seeing the arrangement across all these dimensions, and we're seeing the ordering of this point relative to all others. And that allows us to see that this is an outlier, that this is really a curve, and so forth. And that's the kind of thing that a summary statistic is really bad at. And this is a point to sort of drive home, is that so the thing that you want out of a statistic, the one thing a statistic should do for you is measure one thing, right? A one number should mean one thing. It shouldn't mean a dozen things. Right? And that's what it makes a good measure. A good measure is unidimensional. It ramps up from low to high in an interpretable, understandable way. But by barreling down to a single dimension, it also robs you of understanding the holistic feature of what's there. And that's what visualization does, especially network visualization does, that it can't do by a single statistic, because these are multidimensional objects. And so by having the entire array, we can see something about the arrangement of points that we wouldn't capture necessarily with a single summary statistic. Now, once I see this curve, right, I can go, oh, well, my model's misspecified. I should have a squared term here or some other kind of non-parametric linear term to allow me to capture that curve. But I'd be very likely, if I didn't look at the plot, to just go barreling ahead with a linear piece and forget it, right? So you want to play for that. So ask yourself for a minute, why does a scatter plot work, right? So a scatter plot works. I'm looking at this. It's representing the data. I have an array of an x-axis. I have an array of a y-axis. And each point is a combination of an x pair and a y pair, right? This is the exact same data, right? So this is I've done absolutely no violence to the data here. It's the exact same array, right? I mean, the issue is I've just randomized the y-axis, right? Which is a stupid thing to do, right? You would never do that. That doesn't make any sense, because I lose all the information. But what I've done here is try to highlight that there's actually an implicit bit of information in this piece that you might not pay attention to, which is that the space is meaningful, right? We understand that we expect for a scatter plot that the x-axis is ordered. It's an understandable ordering. And that's what allows me to relate this point to all other points. And so it's more than just the double array of my x and y sequence. It's the x and y sequence put in a space that's meaningful. So from a network standpoint, what's a meaningful space, right? That's really our fundamental problem, because when we lay out networks, we tend to use any darn space that comes around. And each of these are visions of the Karate Club. Is that right? Or is this Zachary's Yeah, I think this is all the Karate Club. And so these are 3 different images of the Karate Club that have appeared in print, right? So these are published figures that have used a circle as the underlying dynamic, something close to that concentric sociogram idea, and then a space Springer and Breder layout. These are different kinds of spaces that should in some way represent reality. Now, what this circle space is supposed to represent, it's hard to know, but if you don't know ahead of time what the underlying space is, what the ordering of the axes means, it's impossible to do the mental geography that lets you relate one point to the other. And so what a good visualization has to do is make sense of that kind of underlying space to do useful. And so what I like to do is really sort of push this analogy of scatter plots onto the idea of social network visualization and take something that really pushes the scatter plot to its limit is something like Gapminder. And if you haven't played with Gapminder in a while, go look at it. It's awesome because it allows you to layer over in the idea that you would in a sort of geographic map sense lots of things about the network in addition to just this axis and that axis. And so it turns out there's a lot more we can do than just have our set. So the benefit to making network graphics is that we can make this, where everything is invisible visible, but in order to do so, we need to provide some way that helps us simplify and understand this already massive data set in a way that we can do so sensibly. And that's what we're going to go to next. Right? So the problem we're trying to solve is to come up with a representation of the space that we can embed networks in that is sensible for the problems we want to answer. And that ends up being kind of tricky to do. And so that's what we're going to try to figure out next. And the reason it's tricky is because networks often represent lots of things simultaneously. And you can't represent them all simultaneously. So you have to pick what it is you want to represent. And so do I want to represent something about a difference between local networks and global networks, something about the multiple relations, something about density or groupedness or diffusion potential or so forth. There might be slightly different versions of a visualization depending on the problem you want to answer. And that's why this is really part craft and part science, and why you need to have a data visualization strategy that matches with your knowledge problem. And that's the artistic part. I can have a visualization strategy that matches a knowledge problem, but I also wanted to have data fidelity. I want to have replication, I want to have quantification, I want to have a way to tie things back to a scientifically meaningful visualization that is more than just a pretty picture, but is also a substantively and scientifically meaningful picture. And so how do we get that? Usually we start with some automated process. As Peter pointed out with group detections, these automated processes tend to be heuristics because these are hard to do well. And we also want to maximize or solve some problem simultaneously. And sometimes these things conflict. So if I have a goal of avoiding line crossing in my graph because I really care about tracing where the edges go, I might not be able to have consistent edge lengths. And so I have to come up with a heuristic that allows me to automatically lay out nodes in a space that highlights the feature I care about the most because it answers my knowledge problem, but does so in a way that's computationally tractable and efficient. And oftentimes those things are at odds with each other. And just to drive that point home, these are all images of the exact same graph using default settings from an off-the-shelf network analysis program. So if I pull off the network analysis program, go to Tools, Visualize, drop down to the first one on the drop-down menu and push the button, I can get anything from a circle graph to whatever this thing is supposed to be, right? And so you get this remarkable array of potentials. And so what you need to do as a consumer, if you want to use these types of things, is see if there's some way to make sense of what these are and why you would use one choice as another. Okay? So what makes a good data visualization? We want to make sure we can build intuition, right? We want to succinctly capture high-dimensional properties of the network, and we want it to be worth the space, right? A picture should be worth 1,000 words. If you can say what your picture is easier than you can draw it, then just say it. I also think that graphs should be pretty, right? They should somehow be capturing. They should invite people to come in and ask more questions about the work, at least at the presentation side, if not at the exploration side. From a good scientific visualization, in addition to those pieces, we need to have the ability to replicate the results, right? When I do an image and I hand you off the code, you should get something that looks at least pretty darn close to what I generated. It might be flipped, it might be rotated, we'll talk about that, but it ought to be fundamentally different, and readers shouldn't draw fundamentally different conclusions. You should be able to ultimately quantify the pieces that you care about, right? So if there's something in this graph, I would love to have a fit statistic, right? So is this visualization actually doing a good good job or a poor job of whatever task I'm giving my visualization. We'll talk about what those might be. And it should be theory relevant, right? So whatever it is you're doing with this network, it should help propel the paper forward, as opposed to just be something that, like someone said the first day, a little piece of eye candy to keep the reviewers happy, right? Though, you know, I'm not beyond that, but that shouldn't be its sole purpose, right? And so, just to give an idea, that first notion of what makes a data visualization effective, a lot of those pieces are style, or what you might call visualization craft elements. It has to do with color and line thickness and different ways you might rotate things or flip things or have a curved edge or so forth. I'm not going to talk a whole lot about that today. There's, if you want to work in that direction, I strongly encourage you to go read Tufte's work, as well as the Grammar of Graphics book. Both of these works are really nice about talking about what makes sort of the craft side of a visualization effective. So this is what the machine spit out. This is what we published. There was a lot of work that went from here to here that has nothing to do with learning. It's all about trying to get a message out that's clear and effective, and having some redundant elements makes that easier. And most of that's not automatic. All right. So that's my general rubric of the way I like to think about networks and visualizations, is that we have this set of problems, there's a theory we need to solve, and we want to get to it by making this link between a visualization strategy, data fidelity, and a knowledge problem. So now what I'm going to do is talk about a handful of the kinds of spaces that we're going to embed networks in and what those mean. Questions, comments, thoughts, concerns? I remember the first day I told you I talk fast. I just can't help myself. And now I'm going on my 5th cup of coffee today or something. So we're ready to go. So in general, in the networks world, you can think about 2 basic types of layouts. There are 2 types of layouts in the world. One type of layout, one axis means something, right? And in the other type of layout, the axes don't mean a damn thing, right? And so, well, they mean something, but not what you might think they mean. So in the general sense, what we care about in the first set of layouts are there's some distinction between top to bottom or perhaps left to right, but one of the dimensions captures something important about the network, usually being a root of a tree or highly central or something, and the x-axis is just used to avoid layout, crossovers and such. So if you want to lay out a family tree or a bureaucracy or something, you will almost always use this kind of a hierarchy or tree-based layout, where I have a root at the top, I follow down the edge, and all the work in the algorithm is done figuring out why to put this node here as opposed to over here. And so there's an edge crossing minimization we want to work on. Now, if instead the alternative notion is what we call a force layout or a space-based layout. And in a space-based layout, what matters is the distance between points is what's meaningful. We're trying to figure out some way to get points that are near each other, that are tied to each other, and that are not tied to each other far apart. And there are a series of algorithms to do that. Now, if I take a rooted directed network and I put it in a force layout, space-based setting, it works, right? It's not an awful layout, but it's not intuitive, right? I'd have to sit through here and look carefully where the arrows are to find the root. Here's a node that has 2 out ties but no in ties, so that's my root. And then I can say, well, that's one branch of the hierarchy, that's another branch of the hierarchy. Much easier to look here, and then I can say there are so many levels, who's at comparable levels, and so forth, right? On the other hand, if I have a set of a relational problem where what I really care about is how clusters of people are close to each other and how different communities might be embedded in the same space, knowing that I put lots of ties that are tied close to each other in the same part of the network is a useful thing to do. And so clustering pops out really nicely in these kind of spring-embedded or space-based layouts, and it's a miserable thing to do in a hierarchy, right? So I wouldn't want to use a hierarchical layout for any kind of a space where I'm really interested in isn't a hierarchy, but it's instead something like clustering or community structure. Right. Now there's a third type of space that we might want to use, which is geographic space. Right? We all live in the world, we know what that is. And so this is a map of, I think this is hospitals if I remember correctly, but I don't quote me on that for certain. And so each point in the network has a geographic center, and we have some connection between those points. And I know that this cluster up here is in the northwest, and this or northeast, and this is in the northwest, and I have some sense of what's there. Now the fifth statistic that you're seeing here is that when you have a space-based layout like this, Remember, the optimal situation is where two nodes that are close to each other are close together on the screen, and if they're not tied to each other, they're not tied in the screen. So what we can do is we can correlate the geographic distance, their literal Euclidean distance on the screen, with their graph space distance. I can say how long would it take me to traverse the graph to go from this node to that node, say geodesic distance or random walk distance or something. And what you hope to see is a high correlation between the geographic distance and the screen distance. And that's what I'm reporting here as the fit statistic. So in this case, the fit statistic, I can do better in terms of a fit statistic of this network if I allow the clusters to cluster as they do naturally. And so I see that little northeast set ends up over here. The northwest set is over here. This is Southern California. Chicago is kind of up here. But the whole network got split around Texas, which sort of pulled the entire thing in. Texas would like to know that, but so it is. And so you end up with this kind of a sense that if you know the network, you might be able to say something about the space, but your audience is going to know this a lot better, right? And so the great thing about a map is that if your audience knows it, then you can exploit that space. And if what I'm trying to do is ask how likely it is for flu to move from Florida to Seattle, it might be really useful to be able to have a geographic network on my set. Now, it turns out that there are other kinds of fixed coordinate systems that are not so useful, right? And so a classic example is a circle layout. Circles were originally used early on when people were drawing networks by hand because it's an easy way to minimize edge occlusion, right? So if I'm drawing a tie from one node to the next, if I only have a small number of points around a circle, I'll very rarely have ties that fall along the edge, and I can draw those up by hand, and it's not that big a deal. From a fit standpoint, it's awful, right? It's really hard to get a good network fit to this kind of a set. Now, you might do something a little bit of a mix between the two, where I allow the network to be laid out first by its, this is just a version of this, so I let it get laid out naturally according to a spring embedder kind of set, and then clump it up based on the clusters I've identified using a community detection or some such. And that might help me see the balance of ties within and between group. So I've used this kind of graph. There are times when it's effective. It's rare, but from time to time it can do some work for you. This is another kind of network diagram that people use. It's called a chord diagram. I consider these the pie charts of network diagrams. They're basically useless. Their goal is supposed to be to help you find the amount of flow from one set to the next. But because it's the circle, it's really hard to know, like, is this any closer to that, which is closer to that or not. And so I've found they're very pretty. They fit the pretty criteria, but they don't necessarily fit much of the information exchange idea. One thing to keep in mind with fixed coordinate layouts like maps is geography is heavily constraining, and the natures of geography are also heavily constraining. So this is a graph of Facebook. It's beautiful, right? It's got this wonderful color structure, this sort of lights at night kind of thing. And what you learn from it is that no one lives in the middle of the country. No one in Africa, in this part of the jungle of the Sahara Desert, have internet. Europe has a lot. China doesn't have Facebook, right? You don't really need this graph to see that, right? It really wastes a lot of ink in order to get that through. And so you want to be really careful that what you're doing with these kinds of graphs, especially when you're using maps, is that you're not just replicating population density, right? And so most of the time what you're doing, especially when you're putting people on a map, is you're really just mapping population density, and anything you want to layer on the top of population density is going to be hard to see. And so you either need some way to normalize by population density, or you need to be really clear that what you're trying to do is highlight a feature of population density that's not there. And so the fact that we don't see anything in China where we should is perhaps telling. But otherwise, it's really just eye candy. That's another, making that point again. All right, so the other piece you might want to think about is how are you going to distort a network. So the algorithms that I've been showing you thus far are all variants on a very simple replication of a physical system. And so what you've done is you've put a spring connecting nodes, pulling nodes together if they're connected to each other, and pushing them apart if they're not connected to each other, constrained to 2 dimensions. You let it sort of balance itself out, and you get some connections of the networks to each other. This is the raw system. Right, so if I let this network just do its thing, balance out those set of springs, you're going to get a cluster here, another cluster there, but the red cluster kind of overlaps with the yellow cluster. The pink cluster is embedded in the side. It's sort of hard to see. So I'm going to cheat a little bit, and I'm going to say that in-group ties count twice as much as between-group ties, and then my network clusters up nicely. Now, that's cheating, right, in some sense. I've distorted the data. So from my data fidelity line, that would be a problem. But on the other hand, from a communication standpoint, if what I really want to do is say this green cluster is fundamentally different, these are Republicans, these are Democrats or some such, then it might be useful to do that. And so that's perfectly fine, right? So you can do that kind of distortion if it's in the service of your science, so long as you tell your audience what you did. Right? It's not a good thing to do. If your audience thinks the world is done this way, if they're reading it thinking all these springs are equal, and you've cheated and turned up the spring on one set and not in the other, then you need to tell them what you did. Right? That's fine. You might also need to spread things out, go the opposite direction, so that you can do a fisheye transformation. So if you have a grid, but you put a little lens over one part to expand it a little bit, that can help you see where there's a knot all tied up. You might be able to open that up a little bit and see something inside that you couldn't see otherwise. So here I've applied a fisheye to the middle of this cluster and another one to this cluster, and that helps me see just a little bit inside there where it would otherwise be occluded, and that's a nice way to sort of generate that. Again, you want to tell your audience that you've expanded relations within groups or something so that they can see, so that they can know what they're seeing. I find curves, this is I find them useless. Gephi uses them to determine direction, so ties go from and then clockwise to received, but in a big graph that's impossible to see, and so it just adds extra ink to the page over a straight line. You might be really tempted, if you're thinking about space, to use 3D graphs. They're cool. Like your audience goes, ooh, right? It's kind of fun to play with. It's much more useful as an exploratory tool than it is as a presentation tool. You just can't use it when you're trying to publish a paper somewhere, even if you have the ability to do movies, because people aren't going to look at them. But the main issue is occlusion again, is that these nodes are behind each other in ways that's really hard to see. So you often get a better fit, like I can fit a multidimensional item in 3 dimensions easier than I can in 2 dimensions, but it's often difficult to do much with. Tufte has this really idea called small multiples, that if I want to compare networks across different sets, what I want to do is take the same sort of thing and repeat it in lots of places. And this is an example that we use in a paper trying to explain differences in disease diffusion potential based on degree distributions. And so we generated random networks, and we discovered that these networks all had core periphery structures. And so since a core periphery structure is always going to be a big tight ball with the corona around it, we just took as a representation a 1/4 slice of each one, and we put it at each point in the space where you have a really high degree but very skewed degree distribution, a relatively high degree but a very unskewed distribution, and it lets you see a little bit about how you can compare one to the other. And this is an idea of a way that you might compare networks one to the set. And then if you really want to go in and look at them in detail, you can pick each one, do the thing that makes your audience go ooh and ah, and then bounce around in terms of this space and say, well, how is one a little different than the other? That's a nice way to do this kind of comparison within a nicely defined framework for your audience to see. Then that's just silly. We already talked about that one. Let's see if we can go to one of these. Is that going to work for us today? So oftentimes, when you go to dynamic networks, you can have slightly interactive networks. And so this is this notion of a spring embedder I told you about a minute ago. But it's interactive, and then I can grab the network and sort of flip it around. These are fun to play with. These are kind of like 3D graphs. And if you really want to get into the system and play with it, it can be kind of cool. But it's really a time waster. There's not a whole lot you can do there other than do that. There are interactive versions of graphs that we can play with that are nice exploratory sets. So this is the Trump network, and it takes a while to load here, but it allows you to go in once it is loaded. You can go into the graph and you can sort of keep drilling down. There's a nice version of this on the Panama Papers. These are ways their most important thing about them is that they allow your audience to dig into the data in a way that they might not otherwise. And that can be a really nice way to sort of suck people in and get them sort of engaged in the process in ways that they might not otherwise do. We've used this a lot when I do consulting work. I almost always make graphs like this for people because an audience that really cares about the people that are engaged can find this it's a very easy way to communicate to them what's in their setting. And I can show some examples of that if people are interested. Again, so this is an example of this. I showed you this graph before. This is the Duke PhD Exchange Network. So each person is a faculty member. They're tied if they've sat on a PhD exchange committee together. We have an interactive version of this one here. And so if you come into this case, you can just explore that by looking around. If you just hover over a node, you'll find people. Let's see. This is oh, are you comp sci or electrical engineering, Jeff? See if I can find you. I'll never find you. Yeah. So you'd be up in this cluster somewhere, I'm guessing. In any event, you can spend all day doing this. It's fun. But it is useful when you're trying to help people with a tool, and they're going to use that tool to somehow explore their own setting, and it can be nice for reflection in that sense. And there are a bunch of these. All right, we did this already. Will this one work? We can use movies nicely. Oh, come on. Oh, that's too bad. What time is it? Really? All right, let's try this now. Seriously? You guys are killing me. Yay, okay. So this is data we have on dynamic networks. Dan McFarlane collected these data in schools. So the teacher is in the middle. Each kid is a box on the outside. If it's a task-relevant tie, it's in black. If it's joking and goofing around, it's in blue. If it's negative, it's in red. And so this is a summary of an entire classroom period. You can see there the teacher just yelled at everyone. The kids are all joking in response. The teacher yells a little more. The kids are still joking. The teacher's kind of losing control here, so he does what you might often do, which is you divide and conquer. And so you send them all off to work in groups together. And that happens about here. Again, so there's no instruction. There you go. So they send them off to do group work with each other, and then they're just telling jokes with each other in the classroom, and they're not doing anything effective. It pulls off 7 there and balls him out because 7's not doing a good job. The teacher thinks he can do something, and then the bell rings and they all go home. Right? This is a movie of a substitute teacher in an algebra class, and as you might imagine, that teacher had no authority and no chance to get anything done. It's very different than some of the other classes where when you look at a class that functions well, there's this rhythm that happens between people going back and forth. Movies are great from a way of being able to analyze these or being able to see these kinds of dynamics, especially when you think about tempo in a classroom or something like that. But they are difficult to see. Come on, duplicate slideshow. They're difficult to see in terms of being able to think through problems in sequence. And that's because humans have pretty poor visual memory for movement, right? So I have a hard time remembering how something unfolded in a sequence. And so if you really want to do static comparisons, it's useful and nice to have the small multiples of windows. But if you want to understand the tempo of a setting and sort of the rhythm of a room, if you will, movies can be quite useful. What else to talk about? So the other thing to do is to think about how much information you really want to show. So we talked about kinship trees before. If you think about what a kinship tree looks like, I have an ego can have a father, a mother, a brother, a sister, and so forth. A father can have a father, a mother can have a father, and so forth. So if you can imagine going each of the 2-step networks through a kinship tree could go from ego to father, it would be my grandfather. I can go from ego to brother to daughter, it would be my niece, right? And so in fact, you don't need to do the entire Morgan-style kinship tree. Instead, you can do a role tree. And so this is what the world looks like out from ego. And so ego has a father who has a father who has a father who has a father, who would be my great-great-great-grandfather, right? My father's wife is my mother. This was done in 1960. She doesn't get her own node. My father's wife's sister, right, would be my maternal aunt. Right? And so you can imagine thinking about your entire kinship structure as a sequence of walks through this space. Right? And this is how, it's not accidental. White was a physicist, and he took notions of semi-groups that are applied and walks on role graphs in order to come up with kinship structures. And this is why this book, this is how he came up with the notion of role relations coming out of anatomy of kinship. Abstraction, though, is helpful, is probably the single best solution to the problem of density in network graphs. And so this is about as big of a point and line graph as you can make reasonable sense of. And even then, the fact there's a particular line in one spot or another is pretty useless. These are nodes. In this case, each node is a journal, and each tie between a journal is the co-citation similarity. So two journals are tied to each other with a high weight if other journals cite them in the same way. And so what you see in this is all social science journals in the Web of Science. And if you look at this, you'll see there are these clusters. Well, here's a cluster here, there's another cluster here, there's another cluster here, and so forth. And that clumpiness comes out of the natural spring-embedded structure of the disciplines. And so if you then layer over these disciplines, you see what kinds of disciplines fall in the different settings. And so along the sort of western coast here, you have the money sort of part of the world. You have economics, money and power, economics, law, and management. Org behavior, which is essentially organizational psychology, is literally the bridge between management and the field of psychology. Right? To the top, you have political science and geography. Political science, political things happen in places, so that makes sense. Political economy is a well-known fact, and sort of the law. So this is sort of the kids who want to go to law school part of the world. This used to be the world around meaning, like anthropology, moving through to education and such. Those of you that know the history of the academy over the last 50 years know that anthropology has essentially exploded. There's not much there anymore, and that's why you find no clusters. Physical anthropology is starting to sort of move around its set. Library science is off in its own world, so this is what's left of the meaning part of the social science space. And sociology fits nicely in the middle. And, that makes us all feel good. We like to be in the middle of things. Until you, do I have it here? The other thing that, before you start feeling too all high and mighty about it though, is to realize that the height of these contours matters, right? So we're in the middle of the world, all right, but we're a little bump. And economics and law and political science and psychology are these giant mountains sort of looking down on us from the outside. So take your pick or what position you'd like to be in that set, but that's there. Now, if you don't have the nodes at all, you can get rid of them, right? You don't need to have the nodes to make this picture, right? And so I can get rid of those. And I do the same thing with natural sciences where there are too many journals to put them on there, and I can just put the contours over the top. And so what's kind of fun about the natural sciences is math and physics likes to think that they're the center of the world, but in fact, they're one part of a large community, right? Everyone uses math, but math as a field is sort of onto its own self. There's the real sort of driving world in the natural sciences anymore tends to be medicine. So you get medicine, biology, and then you get material science, engineering, and math, and the link between them is chemistry. Right? So the thing that links the biological side of the world to the material science side of the world is chemistry. And it's kind of fun to think of chemistry as the structural link between all sets of the natural sciences. And you can do this. This is on lots of different sets. This is another way of looking at Duke. So this is Duke University publications through the scholars at Duke fields. And so you find here's our collider. So our little particle accelerator is off in its own little world. There's a group of people doing HIV testing over there. Chemistry is kind of its own little spot. And this is the medical school. Right? And so just sort of shows you where we're at. There's a problem with this density idea, and this is just finishing up there with what Peter sort of pointed out. A traditional network representation of something like co-voting networks looks like this, right? And it's just useless. And so instead, we can generalize not so much by aggregating up into density, which is what we did here, but we can identify nodes that are equivalent in some way and then just collapse them. So in this case, what we did is we took these dense nodes, and we said instead, a lot of these nodes have exactly the same pattern of ties to each other person. That is, they're structurally equivalent, right? So we can identify sets of nodes that have the exact same pattern of ties to everyone else in the nodes, or everyone else in the network, and then just treat these positions as the elements of the network as opposed to individual nodes. We don't care about each individual node, we care about the positions. And so when we do that, then that allows us to aggregate the network, and that was the trick we used to get this graph, is that each of these points are structurally equivalent positions, and in the bad old days, you'd have a small sort of, we've always had in American politics, we've always had party loyalists, right, which are these positions where they do whatever the party tells them to do. But in the past, party loyalists were cross-cut by other kinds of interests. And so the other kinds of interests means that they would be able to have an opportunity to cross-cut in their ties, and that's gone away in the recent years. And so what's been dominated instead is this pure party loyalty at the expense of being in the middle. All right, so in the interest of time, I'm going to come to the conclusion pretty quick. One of the nice things that Moreno started with that I think would be really fun for people to really work on carefully is coming up with a language, a visual language for networks. And so what Moreno really tried to do when he was drawing these graphs was to be rigorous about things like color and shape and markings, right? So reciprocal ties had a certain language. And his thinking was that they were developing a language of networks. And that's kind of gotten lost in the way we've moved since. There's been some work on it, right? So this was Moreno's original set. The Payuk folks have an idea of thinking about different patterns of relations with different kinds of structures, but it's never taken off. And I think that what would be fun to do as the field develops is to figure out how we might find ways to continue on with that kind of language of networks. And there are some things that I guess, almost by happenstance, we've been doing, right? So size almost always corresponds to something like either centrality or degree. Right? And color's intensity usually has some kind of a scale from low to high. But otherwise, we don't really have the same kind of linguistic cues that are coming out of the markings on the page that we used to have. And I wonder if that might not be worth trying to revive. So I'm going to leave that at that. I'm going to say that the whole point of this piece was to give you a sense of what's out there and ways in which you might do it. What we're going to do in the lab in the last half, about hour and a half of today, is talk about how you might actually implement some of these ideas. I'm going to show you the way to do it in R as best we can, and I'm also going to show you another program, which is the program I use most of the time for visualization, just as a way so you can see what's out there and to play with some of these other kind of things. So I see the coffee showed up, as have the treats. So let's go get a sugar high and a caffeine buzz and come back for another set. Okay?